Assalamualaikum warahmatullahi wabarakatuh. With all due respect to the judges and all the audience, my name is Gilang Pratama Putra Siswanto from Physics Department, Faculty of Science and Technology, UIN Gilang Jati Bandung. Would like to present my work about physics science project with title Lagrangian motion of a dual spring with hang-down pendulum as a part of International Walisongo Science Competition 2025. Let's get rolling.
The system moves in two forms of motion. First is oscillation translation of metal ball M2 between two springs and the movement of pendulum attached to concrete ball M1. The next step that implement is we determine the Lagrangian motion of mass between dual spring with hanging down pendulum. Firstly, we need to find the constraint that applied in the system. The system has two constraints. Firstly, pendulum length constraint. The right answer M1 is always at distance R from M2 that represent as the equation x1 minus x2 squared plus y1 squared is equal to L squared. Also have the constraint is horizontal motion of M2. M2 is constrained to move only horizontally, so the effect is y2 is equal to 0. After that, we ensure the degrees of freedom. The system has 2 degrees of freedom. Firstly, at x2 itself, so the horizontal position of M2 coupled spring. Secondly is theta as angular displacement of the pendulum. The measures of number of independent generalized coordinates need to describe the system configuration. The movement of the system is move translational as the spring for the M2 and swinging of the pendulum at M1. So we need to ensure the Lagrangian motion equation. Firstly, we determine the position of M2 proposed as R2 for the x-coordinate as x2 from the wall or the static that have been attached with the spring through the metal balls. So we could determine that as x2 and the y-coordinate is equal to 0. Subsequently, we determine the position of M1. x1 is equal to x2 plus L sin theta, with sin theta got from the respectively the angle in front of the trigonometry function, where theta in front of it is proposed as sin theta. So we apply the y1 is equal to minus L cos theta because y-axis is positive upward and the system is hanging down, so we need to have the minus sign, and the cos theta is proposed as the side of the angle itself as trigonometric. So we determine the velocity for M1. We determine the x1 dot is equal to x2 dot plus L theta dot cos theta, and y1 dot is equal to L theta dot sin theta, and x2 dot is equal to x2 dot itself. And then we determine the kinetic energy of M2 as T2 is equal to half times M2 x2 dot square, and kinetic energy of M1 is half M1 times x1 dot square plus y1 dot square. So we substitute the value of x1 dot square and y1 dot square, and we apply the trigonometric properties such as cos square theta plus sin square theta. Respectively, we have the equation of T1, and after that we sum the total energy as T is equal to T1 plus T2, and substitute every kind of T1 and T2 component that have been found before, and we have the total kinetic energy. Subsequently, we apply the potential energies that apply or work on the system. Firstly, gravitational potential energy in M1 or the pendulum is proposed at Vg is equal to M1g y1. So substitute the y1 and we have the potential energy. After that, we have the spring potential energy and M2 with assumption S2 is measured from equilibrium position as Vk is equal to half kx2 square plus half kx2 square is equal to kx2 square, with k is spring constant. So we sum again the potential energy from the gravitational potential and spring potential, so we have the total potential energy is equal to minus m1 gl cos theta plus kx2 square. After that, we apply the Lagrangian function proposed as L is equal to T subtract by V, and we substitute the T and V value, so we have the Lagrange function. After that, we apply the Lagrange equation of motion as shown below. d dt dou L divided by dou Q I dot minus dou L divided by dou qi is equal to 0 for qi that eliminate or execute at x2 and theta. Firstly, we execute at equation of x2. We apply the derivation of Lagrange function respective to the x2 dot, and then we derive it again respective to time. And we also derive the Lagrangian function respective to the translation of x2, and we subtract the derivation of dt dou L divided by dou x2 dot subtract to dou L divided by dou x2. So we have the equation for x2, and we do the same for the theta. We derive the Lagrangian function respective to theta dot and derive it again respective to time, and we derive the Lagrange function specifically respective to theta. And then we subtract again the derivation dt dou L divided by dou theta dot to dou L dou theta. We have the m1 L square theta double dot plus m1 and then Lx2 double dot cos theta plus m1g L sin theta. We divide every component of m1 and L at that equation. We have the final equation for theta, L theta double dot plus x2 double dot cos theta plus g sin theta is equal to 0. So we have to find the solution of movement of the system with linearized motion. With solution for small oscillation, we assumption that we have is theta is smaller than 1 radian. Also, we apply the Taylor series, so sin theta proportion to theta, cos theta proportion to 1, theta dot square is proportion to 0. We linearize equation that have been found before for the x and theta as equation 1 and 2. We made it in matrix form as shown below, and we have the assumption solution of the form is in harmonic oscillation. x2 respective to time is equal to a e power I omega t, and we do the same for the theta respective to time. And we substitute it to linearized equation 1 and 2, and we have this equation number 3 and 4. To have the non-trivial result, we apply the characteristic equation. We have to find the determinant of this kind of element is equal to 0. We apply this calculation, and we have the equation is equal to 0. After that, we apply the natural frequencies with assumption of lambda is equal to omega square. We apply it to lambda and equation that have been proposed for natural frequency with omega 1 and omega 2 is equal to roots of every lambda itself, with lambda 1 and lambda 2 are the positive real roots. So we have to find the amplitude ratio from equation number 4. B divided by A is equal to omega square divided by G subtract by L omega square. Also for each omega I, we could determine it as gamma I. After that, we could apply the general solution with physical solution is the real part. X2 respective to time is sigma for EI is equal to 1 to 2 Ci cos omega I t plus Di sin omega I t, and theta respective to time is sigma I from 1 to 2 gamma I Ci1 Ci cos omega I t plus Di sin omega I t, where constant Ci and Di are determined by initial condition. We obtain the specific solution. We apply the initial condition to determine the constant C1, C2, D1, D2 with consider of this point. The initial displacement as x2 from time is equal to 0. Velocity of m2 or c x2 dot t is equal to 0. Initial angle t for t is equal to 0, and theta dot for t is equal to 0. After that, we apply the position equation at t is equal to 0 from the equation number 5 and 6. We apply the equation, so we have this equation, and we differentiate the equation number 5 and 6 in order to validate the equation at t is equal to 0, and we have the equation as shown as equation number 7 and 8. So we evaluate it at t is equal to 0, so we have the x2 dot with t is equal to 0 and theta dot for t is equal to 0.